Chapter 7, Section 3, Question 1. Simplified radical form. You may say, hey, we did simplified radical form back in Chapter 7, Section 1 with even odds, and it was lovely. Folks, look at these numbers. This is not a beautiful number like we had in Chapter 7, Section 1. This is number 50. I know that 5 times 5 is 25, but what do we get with 50? Let's take a look over here on the side. 50 can break up into, it does break up into 25, but 25 times 2. We're going to break it up some more. This is called prime factorization, and you may have used factor trees in the past. And remember that I would like for each line to be equal to the line above or below. A lot of people have their factor trees kind of pruned off, and then they start losing things. So over here, take a look at how 50 breaks up. I'm going to actually take a moment and write it all down. I would not necessarily expect you to do this, but 50 breaks up into 5 times 5 times 2. There are 4 x's. I'm going to write 1, 2, 3, 4 x's, and 6 y's. I'm going to write 6 y's. And this is just to introduce you to this section. Because remember from back in Chapter 7, Section 1, we always looked for pairs. I have a pair. What happens to pairs? It goes on the outside. I have a 2 left over on the inside. I'm leaving this really large space. And then here's the 2 left over on the inside. So the pair comes on the outside once, and the 2 is left on the inside. Then, I have a pair. I have a pair. I have 2 x's on the outside. So I want to write that as x squared. You might also remember from Chapter 7, Section 1, the invisible index number 4 divided by 2 gives you 2. It still works. And then I can look at, I have a pair of y's, a pair of y's, and a pair of y's. I have 1, 2, 3 pairs. I have y to the third. Also, from 7, 6 divided by 2 is 3. Notice that I have an unusually large space here. It's unusually large, but it is important because if these got too close together and that 3 jumped into this index number area, that would suddenly become a cube root, and I don't want that. I'd like to have at least a finger's width in between here. I made this exaggerated because I want to make sure that you are doing it correctly and that those do not suddenly attack each other and that become a y regular with a cube root. I want to make sure that the stuff in the front stays away from this index. A lot of students squish it together so much, I have to mark the entire question wrong. Don't do that. All right, here we go. Oh my goodness, 112. There is a cool rule that you should know. If you want to look at a number and see, does the number, a large number, divide by 4, simply look at the last 2 digits. If the last 2 digits divide by 4, the entire number divides by 4. 12 divides by 4. So I'm going to take 112, and I know it divides by 4. And that goes in there 28 times. I can break up 4 into 2 times 2. And 28 can break up into 4 times 7. Remember that we're going to keep bringing these down because if you lose them and suddenly the problem's wrong, then suddenly you're losing lots and lots of points. I don't want you losing lots and lots of points, which is why every single line should equal the line above it or below it. This is a prime factorization tree. It is useful in so many things. So keep this negative in the front. See that 4 in the index? This number here is where a lot of people are going to get half-pointed to death in this chapter, is they're not going to write the index number. Then they won't use it as a 4th root, and they won't write an answer that has a 4th root, and probably you'll lose the entire points on the entire question. 112 breaks up into 2, 2, 2, 2, and 7. 12 m's. Do I really want to write 12 m's out? Not really. Do I want to write 16 n's out? Not really. So I'm not going to write those guys. If it makes it easier for you, I have actually seen students writing out 12 m's and 16 n's so that they could do the circling thing. If that is what helps you, you do that. All right. I need sets of 4. Here I need sets of 2 because it's a square root. Here I need sets of 4 because it's a 4th root. I have a set of 4. And that set of 4 comes on the outside. Hey, that negative is still there. And I have a 7 left on the inside. Now be careful. If you write it like this, you will automatically lose at least half credit because this 4 disappeared. You have to put it back there. If you do not have this index number, that is where so many people are going to lose half to all their points on every single question in this section. And then, from back in 7-1, 12 divided by 4 gives me 3, so I'll have an m to the 3 out here. And 16 divided by 4 gives me 4, I'll have an n to the 4. Again, exaggerated space, but it's there for a reason. If these got too close together, I might have a 44th root. Would I ever give you a 44th root? I would not, but if you write a 44th root, I will have to accept what you wrote and mark it wrong. Now, if you had to look for even odds, folks, take a look. Just the x's, even, does not have absolute values because we only look for even odds. Just the y's. Is that even, odd? Yes, it is. If we were doing absolute values, you would have absolute values just on the y's. Let's look at just the m's. Is that even, odd? Yes, it is. You would have absolute value just on the m's, just the n's. 4, 16, 4. Even. Nobody cares about even. So, just on even, odd. If you had to put absolute values, you would put them only on your even odds. This semester it should be just 7.1. Chapter 7, Section 3, Question 2. We're going to do simplified radical form. Remember in the last question when we had these index numbers and I said people were going to lose a lot of points by not writing those index numbers? People are going to lose a lot of points by not writing those index numbers. 81, we have to see how 81 breaks up. 81 breaks up into 9 times 9. And hey, 9 breaks up into 3 times 3 and 3 times 3. I have a lot of repeated numbers. That is a wonderful thing when simplifying radical form. So I have 3. This time I really am going to write out all those for the betterment of mankind. Here we go. All those, and then 6 A's. Here we go. 1, 2, 3, 4, 5, 6, and 10 B's. Oh my goodness. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh my goodness. Extend that vinculum. All right. Whew. That is a lot of writing. If you need to do this to be successful, then you do that. Lots of students have done this in the past and saved their bacon in this chapter. Here we go. The 3 in the index says, I'm looking for sets of 3. I have a set of 3. Yay! That 3 comes on the outside once, and I have a 3 left over on the inside. But wait, once again, remember, if this is a cube root and you only write a square root, everything after that is wrong. So make sure that you're writing this index number because so many people are going to forget about it. Notice I'm doing just the numbers first, the 3 on the outside, the 3 on the inside, the exceedingly long space. Then I'm going to look at my A's. I'm again looking for sets of 3. 1 set of 3, 2 sets of 3, nothing left over on the inside, and I have an A squared. Hey, let's check. 6 divided by 3 is 2. Math works. Now, I'm looking for, again, sets of 3's. I have 1 set of 3, 2 sets of 3, 3 sets of 3, and 1 left over. So I'm going to have 3 sets of B's on the outside and 1 left over. Oh no, I need to extend this vinculum out so it stays on the inside. Now, let's take a look at the division. What is 10 divided by 3? Think about it. 10 divided by 3. 3 goes into 10 3 times. That's why I took 3 on the outside. 3 times 3 gives me 9. And with a different color, I subtract. And I get 1 left over. 1 left over. It's like math works. If you can do this long division in your head and say 10 divided by 3 is 3 with a remainder of 1, that's how we do it. Again, looking at this overly exaggerated space that I have left there, but you do have to have saying, I usually say on a regular sheet of paper, about a finger's width worth to keep these away from each other. Because if this gets too close to that, you'll have a 33 root, or you'll have a b to the 33 with a square root. I don't want that to happen to you. I want you to keep those with their exponents away from the index number and these things. But it doesn't have to be like a whole hand's size, just usually like one finger's width worth. I am making this very exaggerated because it's our teaching video. Chapter 7, Section 3, Question 3. Do you know that we've been preparing for this section since Chapter 1? We actually had the same problems back in Chapter 1 and in previous math classes, but we just made them a little trickier on you. The important thing to do is reduce first. That will make it so you can recognize them again. If I divide 108 divided by 3, remember groups first. We're going to do the insides first. If I divide that, I will get 36. Hey, the square root of 36. You've come this far in math to do the square root of 36, which is 6. Now, reduce first. Because this is such an easy problem, you had better show me that reduced step before you find the answer, or I will take off a half credit. Because these are very, very nice problems. So I need you to see that you reduce first, that will give you half credit, and then I need to see the answer, that will give you the other half credit. Some students say, I can do that in my head. Well, you'll only get a half point for that. Over here, I can't reduce that, but I can still do the problem. What four numbers all the same multiply to give you 1? What four numbers all the same multiply to give you 625? You might not know that, but you might remember from a previous problem that 625 breaks up into 25 times 25, and those then break up into 5 times 5 times 5 times 5. So the fourth root of this, you're going to break it up into 4 pieces and pick one of them. That is your answer. This is the only problem that you don't really have to show work, although, hey, that might be the work that you would show for this. All right, now, this is to show you that you can reduce even when we have a cube root on top and bottom, or if we have it as one big honking fraction inside of there. So it works the same way. I'm going to reduce the insides with the insides. 3 over 81 is going to give me a reduced form of 1 over 27. What 3 numbers all the same multiply to give you 1? What 3 numbers all the same multiply to give you 27? This is something that we gave to you back in Chapter 1. All we did was we took these and multiplied them by 3 on top and bottom. Your job to make Chapter 7 work is to reduce those fractions first, then find the answer. If you can't, then hey, break that down anyway and find the answer. Reduce it first and then find the answer. On some of these, you're going to get a calculator version of this, where we're going to give you really, really large numbers. Something to think about is you could actually put into your calculator 3 divided by 81, and then press Math, Enter, Enter. That will give you 1 divided by 3. If you have one of the newer operating systems, to put in 3 over 81, you could hit, I believe it is alpha and y equals, and pick the first choice, which is numerator over denominator, and that will give you a way to enter in as 3 over 81, in which case you can just hit enter, and it will give you 1 over 3. So if you enter it as a fraction, it will give it back to you as a fraction. If you enter it as a number divided by another number, it'll give it to you as a number divided by another number, as long as you tell it, Math, Enter, Enter. What this does is the first thing on the math table, column, whatever, instructions, is change it to a fraction. And by entering, you select it, and entering as you do it. So that's how you change something into a reduced fraction. I wouldn't expect you to need it on something this small, but when I give you a 4-digit number over a 4-digit number, you better bet this is a really nice way of doing it. Chapter 7, Section 3, questions 4 and 5. Questions 4 and 5 are basically the same thing. They get yuckier as you go along, but basically they're the same problem. Again, notice all of these fractions. Folks, just like last question, reduce first. Reducing first we should not have to tell you. However, we have been trying to remind you because if you don't reduce first, you can get a horrifying mess over a horrifying mess. And that's not the point of this. The point of this is that we actually do know how to do these problems, and we've been doing them for a while. Our job as your loving yet evil math teacher is to make them yucky so that you think you don't know how to do it, but then, through the miracle of reducing fractions, you can. Did you know that 81 over 144 reduces? Try it. Pause the video if you have to. All right, so what you're going to find is that this becomes 9 over 16. And now, this beautiful problem, I could have given this to you back in 7.1. The square root of 9 is 3. 4 divided by invisible 2 gives you a 2. 16, the square root of 16 is 4. And 10 divided by 2 is 5. But if you think about it, back in Chapter 7, Section 1, we had even, even, odd. We only check it on variables. Only on variables where the entire thing came out, and only on even, even, odd. Just the A's. Even, even, even. We don't care. Just the B's. Even, even, odd. These would have absolute values. Right now, we are not doing those on anything other than 7.1. Over here, take a look. 3 over 64. Does 3 go into 64? There is a division rule for 3s. You can add 6 plus 4, which is 10. Does 3 go nicely into 10? No, it doesn't. So this will not reduce. 3 will not go into 64. Hey, remember that index number. A lot of people are going to forget to write the index number. They're going to square root this because they know that the square root of 64 comes out nicely. Then they'll get everything wrong. So be careful. Make sure you have those index numbers. 3 and 64 are going to stay right where they are. We're going to handle those later. These have negative exponents. Remember from Chapter 1, Section 5, the negative exponent says it's going to go to the other side of the vinculum. From the top to the bottom, it was negative, and now it is a positive 9. This was on the bottom, it goes to the top. It was a negative 6, it's now a positive 6. And now we are going to cube root. Are there 3 numbers all the same that multiply to give you 3? Be careful, some people say the answer is 1. 1 plus 1 plus 1 gives you 3, but 1 times 1 times 1 does not give you 3. There's nothing you can do with this, so that's just going to stay there as the cube root of 3. Then we're going to do 6 divided by 3 is 2. That has to go on the outside. Remember again, that small space in between here. Now, 3 and 64. Can 64 break up into 3 equal pieces? Yes, it can. And then 9 divided by 3 gives me 3. Then, if we were back in Chapter 7, Section 1, we would check for even, even, odds, and we would look at that, and that's odd. So even if you looked at just the x's, that would start off with an odd. If you looked at just the y, that would start off with an odd. You can't get an even, even, odd when it starts off with an odd. So some students have noticed that you always look at that, and what they did was at the beginning of their tests and their quizzes, they made little like highlighter dots on the ones that could be an even, even, odd. And then on the ones that weren't, they just left it alone. So that when they were taking their test, they would be like, there's a little highlighter dot there. Let me go back and check for that. Reducing again. 625 divided by 5. We are again going to have that cube root. Make sure that it stays inside. If you had written the cube root further out, what you can do is give it a little diving board so that it's still part of the hook for the index number. 625 divided by 5 is 125. X to the 2 sevenths on top and x to the 2 sevenths on the bottom. We cancel out and we get y to the negative 27. That is unhappy on the top, so it goes on the bottom as a y to the positive 27. Wow, my vinculum is really long out here. Oh, how nice. You will get half credit for getting here. But then, what's the cube root of 125? That is 5. And then 27 divided by 3 gives you 9. That starts off odd, so we don't have to check out our even odds. And that is your answer.